I'm Dr. Troy Townsend. I'm a chemistry professor at St. Mary's College of Maryland. And I'm here today to talk to you about the states of matter, and we're going to do a demonstration with water. I have my good friend, Bailey, who has agreed to help us today. And she had a really excellent science teacher, so we know that she's prepared and ready to answer questions and tell us what's going on with this. So on my table here, I have a hot plate. This thing can get really hot, up to 500 degrees. I can turn the dial. And on this side, I've got a bucket of ice water. I have some personal protective equipment. So why don't I start by doing what every scientist would do in a lab and protecting myself. So I put these on to protect my eyes. And I have these. You seen these before?
Only really at the doctor's office.
At the doctor's office, yes. The doctor wants to protect themselves from the patient, and the patient from the doctor. And in the chemistry laboratory, the scientist protects them from the chemicals, and the chemicals from the scientist. And I also have here a lab coat. Yes.
This is tie-dye lab coat.
Shouldn't it be tie-dye? What's better, white or tie-dye?
It's white, so it can be tie-dyed.
That's what I think. Any color white should be tie-dyed. So I'm wearing this, and what does this do?
It will protect you if any chemical gets on you.
Right.
If anything, it's like your first layer of protection.
Right, and I can take it off if I have a spill, and I'm back to normal. All right, and I also have this. This is something you would use to hold something hot, so I can grab hot things with it. So today, we're going to talk about the different states of matter, solid, liquid, and gas, and they're all going to be water. So first of all, I'm going to start out, and I'm going to put a little bit of water in this soda can. I'm going to put it on this hot plate.
Whoa, you can hear it sizzle. That's evaporation.
Yep, you're right. Can you tell me more about evaporation? I'm actually going to get two started here.
That actually sometimes has to do with the weather.
Yes, because we have water in the air, in our atmosphere.
We kind of learned about it more clouds than the actual chemistry and all that behind it. Mm-hmm. We learned more about rain than the actual water.
Mm-hmm. Yes, well, the same chemistry that happens in the atmosphere is the chemistry that we're going to talk about today. So we have ice, we have liquid water, and then I'm heating it up. And you said when you heat up ice, you form a liquid, and when you heat up liquid, you form, I think you said a gas. Yeah. So what do you think is going to happen inside these cans?
Eventually, they're going to be empty.
Okay, we'll see. We're actually going to do some experiments. So you get to hypothesize what's going to happen, and then we'll see what actually happens. What else do I have here? Oh, a question about how much space things take up. Comparing ice, solid water of ice, and liquid water, do they take up about the same space, or does one take up a lot more or less? What do you think about that?
Well, it's kind of like if you compare a bucket full of rocks to a bucket full of sand. Mm-hmm. A bucket full of sand, there's less gaps between a bucket full of rocks. So I think in liquid would take up like all the corners of it, and it would take up more space, but it wouldn't actually be more matter.
I really like that image. And I think that works well here because the liquid, like you said, they teach you in school that it takes the shape of the container. So you can pour a liquid in and it just goes wherever the container is. But a solid, kind of like you said, rocks would fall in and they wouldn't really care about the container.
They wouldn't move.
Right. And then, so between a solid and a liquid, they take up about the same amount of space. The liquid fills the container, but the same amount of space, basically. What about a gas? What do you think about a gas?
I think the gas would, unless you put a cap on it, it would actually not even stay inside the container.
Okay.
Gas is like literally everywhere.
Mm-hmm. Yeah, you're right. So in here, I'm heating up the liquid, and you said it turns into a gas. Mm-hmm. And I've got an open can on purpose because what would happen if the can was closed and we heated it up? What do you think would happen then?
It would pop because I think the matter expands or something like that.
It does. Yes, you never want to, this is a safety video. By the way, I should say, don't try this at home unless you're with a parent or a a scientist who's done this before. And also, never heat up a container that's closed because, like Bailey said, it will explode, and that's very dangerous. So we've got these cans open, and I'm waiting for something. I'm looking close at the cans, and I'm waiting to see something. I don't see it yet. What do you think I'm waiting to see?
Something come out of the can, maybe?
Yeah. What do you think is going to come out of the can?
Steam, maybe? Perhaps?
What's steam?
Steam is another form of water.
Mm-hmm. Well, we know there's this couple states of matter, of water. There's solid, liquid, and gas. Which one do you think steam is?
Gas, right?
Yeah. And the reason we can see it is because the gas actually formed into little tiny liquid droplets that you can see. Otherwise, it would be invisible. So that's what I'm looking for. So let's talk about gas real quick while we're waiting for that to heat up. When this comes up and heats up into a gas, where is this going to go? Does it, you said it comes out of the hole. Does it go straight up into the ceiling?
Well, it depends on how dense the gas is, right?
Mm-hmm.
It will go up if it's less dense, but if it's more dense, it'll go down.
You must have had a really nice science teacher in school. So you're answering all these questions correct. So yeah, this gas right here is hot. And so it's going to come up, and as we know, heat rises. So it's going to come up, and it's actually going to spread. And I think you already mentioned this. It's going to go over the entire room. So the water that's in here is actually spread across the whole room right now. It's everywhere.
I'm starting to see it. I saw a little splotch.
Oh, I see it too. Okay, I think we're ready. So what I'm going to do is I'm going to take this, and I'm going to flip it upside down in the ice water.
What do you think's going to happen?
I don't know. That's why I was about to ask you that question. What do you think is going to happen?
The water or steam might cool down really, really quickly.
Okay.
You think the steam might turn to ice?
I don't know.
It might sound like a stupid question, but...
I don't think it's a stupid question. I think it's a great question. So I've never done this before. Let's see what happens. Okay, ready?
Ready.
I'm nervous. All right, I'm going to grab it. It's hot. Flip it over. Oh!
Whoa! What the?
I did not put that much water in there. What happened with that? Do you have any ideas? Were you expecting that?
No.
Okay.
Maybe the gas was expanded, and then when you was in a bigger form, then when you did that, it all sucked in, but there was no thing to suck in.
What does suck in mean?
Like,
how would it do that?
It got less together, the molecules got closer together
Yes,
instead
they
of,
definitely did.
but there wasn't enough air to take inside the bottle, so the bottle had to form to go with it.
Mm-hmm. Yeah, that's right. So like we talked about the spacing of the molecules in the solid and the liquid and the gas. Here we took something that was a gas, and did you say that the molecules were spread apart in the gas?
Yeah, because it got hotter. I wonder why that is.
Well, probably because they have a lot of energy, and they molecules bounce against each other, and that's why they spread out so far, is because they're moving so fast. So inside the can, they spread out so far, separated so far, and then when we put it in the ice water, what happened? I think you already said.
It's sucked in.
I'm going to do it one more time because I think this one's ready. Hopefully it's ready. Ready? Oh! Notice I just put a tiny bit of water in there, and you said it sucked in the water for some reason.
Because there wasn't any, it was either the can was going to crunch more or it was going to suck in something else to replace it.
Okay. So when you say it sucked it in, what do we call that? At home, something that sucks things, or in the lab, we have things that suck things?
A vacuum?
A vacuum, that's right. So it actually created a vacuum inside the can, and the can could not handle it. So it crushed itself. Because why? Why couldn't it?
That's one way to crush a can.
Yeah. What do you think would happen if I took this can and I put it in right side up, like that?
it would have air to suck in. It might crunch a little bit, but
Would it crunch?
maybe. I don't know.
Hypothesis, yes or no? Crunch?
Maybe.
Maybe. So right now it's really hot inside the can. The water molecules are expanded, spread apart, and then when I put it in here, what happens to the temperature?
It implodes.
Implodes, right? And the temperature goes up or down?
Down.
Down. Temperature goes down, and like you said, air molecules are going to come rushing into the can, but we don't think it's going to crush.
That's only if the air molecules can't get in there quick enough. It might crush.
Right. Let's find out. Should we do it?
Yes.
Experiment number 2. I'm going to take this can and put it in directly as is without flipping it over.
Don't burn yourself.
Okay. Ready? I'm scared. Okay.
Ready? Huh?
Nothing happened. There's a little bit of water in there because I put a little bit of water. Not a lot, right? Look, that's how much water was in there.
Most of it turned into glass.
It didn't do anything. Let's put a little bit of water back in there. So our hypothesis was correct, right?
Mm-hmm.
And we think that air came from our atmosphere and went straight into the hole and it didn't crush. So here's the question. Why does the can crush when I turn it upside down?
Because it doesn't have enough air to come in.
It doesn't have any air. Yeah, I cut off the air by having this water surface here.
But that makes me question,
Mm-hmm.
why doesn't the water just come in instead?
I think we saw that. When I turn the can upside down,
Yeah, but it still crushes.
it still crushes. And it also sucks water in. But maybe it doesn't suck it in fast enough.
Like my theory if the air couldn't get in there fast enough.
Exactly. In this case, air does, because air can move really fast, but water is slow.
Do you think the air that was coming in like moved faster and got warmer?
Oh, definitely. Yeah, I think it definitely heated up. And I think it melted some of the ice around it. Okay. While we're waiting, do you have any questions for me about this experiment or about being a scientist or anything about science in general?
Do you think that we would have a different result if we put it in liquid nitrogen instead of just cold water?
I think we would. I really do. Well, liquid nitrogen is really cold. What do you think would happen if we had something really cold here as opposed to just ice water?
It would go really, really, really crushed.
Yeah. Do you know what temperature ice is?
Actually, no.
Well, as it turns out, in chemistry, we have numbers that go with temperature, and somebody came up with a great idea to keep the numbers simple. And so they set everything to water. So water's temperature is actually 0 degrees Celsius, and we know that boiling water will only stay at 100 degrees. It will never go up or below 100. Okay, I think we're ready to do these 2 cans. Should we do it?
Yes.
Okay, this time I should turn it upside down, right?
Yes.
Okay, here we go. I'm going to try to be real
Do it
fast.
really, really quick.
Real
Really quick.
fast.
Really quick.
Okay, get this ice out of the way. Here we go. Ooh. Oh, that was really good.
Oh, yeah, that was
Look
a
how
good
thin
one.
that is.
There's not even any air left for the water to get out.
And not a lot of water got in.
Yeah, and you trapped ice in the top.
Here, I'll let you look at that.
Is it hot?
No,
Promise?
I promise. Okay, here goes another one. The next one, we're going to do this really fast too. What do you think is going to happen? Is it going to crush or not?
It's going to crush if you put it upside down.
Yeah, that's what I want to do. Crush.
Crush it.
Okay,
Be like Hulk. Science Hulk.
here we go. Hulk.
Science Hulk.
Whoa, that
was a good one.
was a good one too. Okay, well, thank you very much, Bailey, for your time today and for helping out with this. And I'd like to conclude just by saying that science is cool. And we were able to take water, which can take 3 states of matter, solid, liquid, and gas. And we were able to see what happens when we put liquid water into fragile container, and we turn it to a gas, takes up a lot of space, and then we flip it upside down and really quickly condense it back to a liquid, and it creates a vacuum and crushes the can. So if you want to try this at home, you should, but you should do it with an adult and someone who knows what they're doing.
And protective gear.
And protective gear, yeah. Goggles, lab coat if you have one, and some gloves. So thank you very much, Bailey, and it was a pleasure to be here today.
You too.
Thank you.